So basically, regression. Hello.
Yes, sir. Yes, sir. You are perfectly audible.
So basically, regression is used to either make predictions or explain. If the objective is to develop a theory, for example, or some explanation, then explain certain kind of regression model should be used, which is called standardized regression. And if you want to make prediction, we use unstandardized regression. So this will be clear as we do the analysis later on. Now, multiple regression analysis or any regression analysis can be used as a descriptive tool and as an inferential tool. As a descriptive tool, for example, we can predict things, we can provide interpretation or explanation, and do complex multivariate relationships, which is called path analysis. Generally, some of you might have heard of the terms structural equation modeling, which is a combination of factor analysis and regression analysis. So measurement errors are generally present in factor analysis, and regression errors are present in regression analysis. But structural equation modeling takes care of the errors of both kinds. It can separate out both the errors and it can eliminate those errors. That is the advantage of doing structural equation modeling, and that will form a part of our next session. As an inferential tool, in inference, basically from a study of some sample of population, you make inferences about the population. And when we do regression analysis, we get certain parameters or coefficients, and these coefficients now should be tested for their significance and whether these will apply also to the population, and whether they can be generalized to other samples, other populations. That is the idea about inference making. Now, most often used hypothesis in multiple regression analysis are there's a linear relationship. So we'll be doing multiple linear relationship analysis right now. Although multiple regression analysis can apply to nonlinear also, but we'll use certain technique called ordinary least square solution. In OLS, we make this called OLS, ordinary least square solution, OLS, and this makes certain assumptions. We'll look at these assumptions. So this lecture will confine to multiple linear regression analysis. Other regression you might have heard of are the logistic regression analysis or polynomial regression analysis and various other kinds of analysis where the linearity is defined in a different way by transforming the variables. Say we take logarithm, etc. And that's a different thing. So we'll not be talking about nonlinear regression, and we'll not be talking about, therefore, like something like logistic regression, which is appropriate to machine learning, for example, and in other areas where we want to predict whether certain people will buy certain things given certain conditions, or doctors may be interested in finding out whether somebody will have tumor in the coming 1 year or half year, depending on the present condition, and so on. So the dependent variable there is a probability. Whereas here in multiple regression analysis, we assume that all variables are at least the interval level measurement. So interval or ratio. But if they are nominal, then we use a different technique where we convert the nominal variables into dummy variables. I think during my first session, I had asked you to go through the dummy variable. Today, when we'll do some analysis called the mediation and moderation analysis, we'll see an example of dummy, or maybe in some other context. I don't remember exactly whether I'll do it today or not, but I'll do it in some situation. Now, the first thing, let us understand bivariate regression analysis, because if we understand bivariate regression analysis, whatever we understand here, we can extend it to multivariate regression analysis. In bivariate regression analysis, the purpose is to estimate the population regression function. This is called PRF. Population regression function means that we want to identify certain regression parameters, or these are also called beta coefficients, beta naught and beta 1. For example, in bivariate, we have one dependent variable y and one independent variable x. And so I have written it here as x1. So this is a function that we want to estimate from a study of the sample. So sample equation can be written as y hat. Y hat means the predicted value of y. So wherever you would see a hat over the particular constant or variable, beta coefficients, etc., these are the estimated values, or these are the values that are predicted. So over x1, there is no hat. So x1 is an observed value. Therefore, we are not estimating it, but this is given to us. This is an independent variable. So y is called the dependent variable, x is called the independent variable. Now, there is a confusion at times with many people who do regression analysis. They think that regression analysis tests causality, but it does not. We call them dependent and independent variables just because there is a mathematical relationship that is described in the form of dependent and independent variables. But by that, it does not become a causal relationship. For a causal relationship, there are conditions which the variables must satisfy. So you should look at the conditions for causality, concomitance, they should happen together, ordering. For example, the dependent variable should appear after the independent variable, and so on. So causality must satisfy certain conditions, and if variables satisfy those conditions, then only to some extent we can say that we are testing causality. But generally, regression or structural equation modeling, there's a myth that people think that they can test causality. They do not, unless in the theory we are saying that there's a causal relationship. So I think in the first session, I had indicated that if research is theory driven, then it is very good, very strong, because then certain things can be hypothesized and they can be tested through analysis. Now, y minus y hat is called the residual. So what is the observed value? Y. What is the estimated value? Y hat for a dependent variable. And generally, y hat will not be equal to y. So for a given respondent, for example, we take the measurement on dependent variable and we find some value. But the estimated value will not be that, will be slightly different, and therefore there will be a residual. This residual is the error of measurement. The estimated regression equation from the sample data is of the form y is equal to a plus bx, simple. So when we'll estimate an equation, we'll write the final result as y is equal to a plus bx, where a is the intercept and b is the slope. This is the equation of a straight line. If you have done coordinate geometry in your school time, then this is the simple equation of a straight line, where x is the independent variable and y is the dependent variable. Now, so in bivariate regression, certain concepts let us see, and these concepts will also apply to multivariate. The key problem in regression is to find values of the coefficients a and b following the ordinary least square solution. As I said, we'll follow the OLS. It is called ordinary least square solution because we minimize the square of the sum of the squares of the errors. So suppose you have taken 10 respondents in your study. For 10 respondents, we will get observed value of y, and for each, we will also get estimated value of y. So there will be 10 errors. For each individual, there will be an error, y minus y, I minus y hat. There will be 10 errors, and if we square them and sum them, then this is the assumption, this is the condition that we put on ordinary least square solution. That is, the sum of the squares of the errors should be 0. So should be minimum, should be smallest. And there are various ways of showing, if we assume this, then how A and B can be determined from this. I'll not go into that because you write certain normal equations, which is an easy way, or you can do some differential analysis where you find first derivative, second derivative, show that the first derivative 0, second derivative is positive, and so on if you have done some the differential equation. So I do not want to really involve you in deep mathematics, but basically we can determine from this condition, we can determine the values of A and B. Now, we can, what is the sum of square? So this residual sum of squares is called the sum of squares RES. And if you remember in doing factor analysis, that lecture, I have said that total variance is equal to some true variance, some error variance, and so on. Now here we write that equation. That is the fundamental equation. So again we write this equation in the context of regression. And we say for y, sum of square of errors for y is equal to sum of squares for regression plus sum of squares for residue. So regression, that means if the regression, the amount of variance in y that we can explain on the basis of the regression equation is called the explained variance. And the variation in y that we cannot explain on the basis of the regression model, that is unexplained variance. So these two variances are present in the regression model. Total variance in a regression model is the explained variance, that is explained by the coefficient beta, for example, for beta 1 here in this equation, or B, let's say in this equation B, and whatever is unexplained therefore is that goes into the residue. I'll again suggest please always go through the textbook to just make this background solid. So B is called unstandardized regression coefficient, and if we regress x on y, then the value of B will differ from that if we regress y on x, because x may have certain standard deviation or variance which will be different from that of y, and therefore what we are regressing on what, that will determine the value of B. So if we write B yx, that means we are regressing y on x. If we write R or B xy, that means we are regressing x on y. We call it regression models because we are regressing on something. Regression is a term which can apply to various domains. You might have heard of, oh, this guy has regressed to his childhood. That means this person is behaving like a child. That means he is not able to come out of his very early childhood behaviors or very early childhood thoughts. And regression is a kind of clinical statement about individuals. Clinical psychologists generally use regression in that sense. So regression means falling back upon something basic. So we assume that x we can always measure. It's an independent variable. It is basic. And what we cannot measure, what we can determine on the basis of this because of certain relationships, therefore we are regressing that which we cannot measure, determine on x. That is why it's called regression. So you can look at these equations, y hat is equal to beta x. Now here I have written the equation in the standardized form. In the standardized form there is no interval. I'll make it clear when I do the analysis. We'll see that interval in a standardized regression equation is 0. And why it is 0, we'll look this clearly in data analysis. And for a bivariate regression analysis, R is nothing but multiple regression coefficient, capital R. And in a multiple regression equation also it will be capital R. Capital R means that we write something like R. Let me write it here just to show to you. R, let's say y, ry dot x1, x2, x3, etc., depending on how many, whatever x you have. This is called multiple regression. That means all of these, we find the correlation between the dependent variable and all of the all the independent variables together. That is why it is called multiple regression. So these dots indicate that we are taking x1, x2, etc. all together, and we are finding their correlation through to y. If we found R yx1, this is simple bivariate correlation coefficient ryx. So ryx in bivariate regression, the simple correlation that we get between y and x, that is the multiple correlation, because we have only just one independent variable, one dependent variable. But if there are many independent variables, then that means that we are taking them all together and it becomes a multiple regression coefficient. So it's simple to remember. If you have just two variables, you will get bivariate correlation or regression or whatever. But if you have several independent variables and one dependent variable, then the correlation between the dependent variable and all the independent variables taken together, that is multiple regression. So multiple correlation. So if we understand this concept, that is what we'll see whether the model is strong or not. It is explained as R square. R square is the coefficient of determination. How much percentage of y, variation in y, is determined by the variation in x. That is how we define simple coefficient, this correlation coefficient. That's the general way of really inferring how strong is the relationship between the two variables. So higher the value of R, actually R square, therefore by squaring it, more strong is the regression model. So you can look at these, relationships between beta yx and beta xy. You can see by this equation at the bottom. So this can be understood on the basis of their differences in standard deviations, because y and x have different standard deviations. Therefore, the b xy will be different from byx. Now let us see bivariate regression equation. Let us go to some further understanding. Prediction, use unstandardized regression equation. I have been saying this. Explanation, use standardized regression equation. How to get unstandardized and standardized? We'll see all this when we do actual analysis using certain data. So if we have standardized regression equation, we can make an important decision about the relative strength of the variables. If there are two variables, which variable is more important, or which variable is stronger in determining the value of y, which independent variable is stronger, that statement can be made. But we cannot use a standardized equation for prediction. For prediction, we'll use unstandardized regression equation. But there we cannot make the statement which variable is stronger. So let us understand it very clearly. What is our objective? In fact, most of the software will provide both unstandardized as well as standardized. Then depending upon your need, you use a particular regression model, unstandardized or standardized. If your objective is to develop an explanation, a theory that relates certain variables, then you would like to find the relative strength of the variables, which variable are stronger. Generally, a theory should be able to say that. But if your objective is to make a prediction, you use unstandardized regression equation. R square is the coefficient of explanation or explained proportion of variance, coefficient of determination. And therefore, 1 minus R square, since we have standardized our variables and explained in standardized equation, therefore, total variance will be 1. So we go back to the discussion that we had in case of the factor analysis, where we normalized the total variance into 1 and we divided that 1 into h square, s square, error square, and from there we determine the reliability of a variable or a scale. So if 1 is the total variance, then 1 minus R square is the unexplained proportion of variance. Very simple. If we can find out R square, higher the value of R square, stronger is the model. But if we get higher value for 1 minus R square, then model is weak. So one concept is whether the model is strong or weak. This is the strength. Is the model significance? Can the model also, can from this model be inferred something about the population? That is testing the significance of R square. How significant is R square? So there are two questions that we'll answer by doing regression analysis. One is the model significant? R square should be significant. Is the model strong? R square should have a high value. To test significance, we'll find the F statistic for the model, and to see whether it's strong or not, we'll simply explain on the basis of R square. So these are the 2 points we have to keep in mind. Higher the value of R square, stronger is the model relationship or the model. And if the F ratio is significant, say probability less than 0.05, then we say that the model is significant, can be generalized to population, etc. Then here, standard error of estimate is what is important. There is an estimate of the absolute amount of variance unexplained. How much variance are we not able to explain in the data? Again, so standard error, if you remember, how was it defined? Standard error is the standard deviation of the sampling distribution. You should remember those definitions. I think in the first lecture I defined those terms. So standard error is the standard deviation of the sampling distribution. So each of these beta coefficients will have a sampling distribution if we take a sample, and if we take a different sample, the value may change, and we take 2000 samples from the same population, then how those beta coefficients are distributed, that standard deviation will give me the standard error. But in practice, we don't do any study on so many samples. So we estimate it. So we will estimate standard error of the estimate of beta on the basis of whatever results we have got. So again, we'll see that. And simply on the basis of the obtained data for a sample, we can compute SEE as SS residual divided in -2 square root of this ratio. So degrees of freedom is n-2 in bivariate regression, where n is equal to number of observations. So if we take 10 observations, then regression model, this regression model will have n-2, 10-2, 8 degrees of freedom, etc. And again, if you remember the definition of degrees of freedom, you should be able to derive these degrees of freedom for any regression model. So SEE provides the average error in predicting Y from the regression equation. So if we can find out this, we can find the average error. And since all this will be available when we do analysis, then the problem is simple. Actually, you don't have to compute. Most of the things will be done by the software, but you have to have an idea of these. Then there are certain confidence intervals. Confidence intervals are for different levels of significance. Let's say they can be a 95% confidence interval, or they can be 99% confidence interval. 99% confidence interval would mean that our alpha value is 0.01 probability, or 95% would mean that our alpha value is 0.05. And if we assess the confidence intervals, this interval can be used to say whether or not null hypothesis is rejected or accepted. Again, I'll explain this when we get actual numerical values in the data analysis. So remember, significance of the model is tested by significance of R. Significance of the model is tested by the significance of R. Where is R? I wrote it something. Whereas significance of the coefficients B is tested through t-test. So this is the only difference. Is the model significant? Do an F-test. is a regression coefficient significant? Do a t-test. So for each regression coefficient, there will be a t-test. For example, if there are two independent variables, x1 and x2, and y can be written as beta 0 plus beta 1 x1 plus beta 2 x2, as in multiple regression equation that will come to. There will be a t-test for beta 1 and there will be a t-test for beta 2. Each, it is possible that one of the regression coefficients is significant, the other is not significant. So that also we'll see later on. And then in the SPSS output, because some of you may be using SPSS output, there will be a beta and there will be a B. B stands for unstandardized regression coefficients. Beta stands for standardized regression coefficients. So when the standardized regression coefficients are reported, you will see that against the interval, against the intercept, there will be an entry 0. We'll see this in the output when we do the analysis. Suppose you have this data matrix, simple data matrix, and source is tag 2007. I have taken these data from there. Then this data matrix, first of all, we can have a visual inspection if it's a small data. We find that the observation number 10 and observation number 6 and 7, they are almost like outliers. They are very large values. So there appear to be 3 outliers in this data set. But for a large data set, we cannot do a visual inspection of the data, so we cannot say whether there are some outliers or not. So there should be some analysis which should show us whether certain values are outliers. I think if you remember in the previous session, we did outliers by using the MVN package. Again, we'll do it today. We'll use this data only. And I did analyze this by using the Excel sheet. So if you do multiple, I have done it for one of the variables, that is x2. So I have taken a bivariate regression. I have taken just x2. So this is the simple result. You can see that multiple R is 0.933. These are the regression statistics. And R square is 0.87. So 0.87, R square 0.7 means that the model is strong. There is a strong relationship between, because it says that about 90% of the variance in Y is explained by x2, the variable 2. Normally, we should report adjusted R. Adjusted R is obtained because depending on the number of variables and number of subjects, so adjusted R is an R that we obtain by correcting for number of variables and number of subjects in the data. So here adjusted R is 0.76. So adjusted R square will be about 50%, 51, 52. You square this and you will get adjusted R square. On the right hand side, you can see the adjusted R square. Adjusted R is 0.05 for regression statistics for x2. And this is, the ANOVA tests are given here, and the standard error is given here, and we'll then see, what is happening. The models are, if you can see, there's in the first analysis against the intercept coefficient, below coefficient, it is 0 at the left bottom table where it is reporting intercept. So the intercept is 0. This means this is a standardized regression equation. And therefore, because it is 0, this is not tested for significance. But for x2, the coefficient is 1.456. Therefore, simple equation, standardized regression equation will be y is equal to 1.35. Please write it as y is equal to 1.456. So this will be 1.46. Make that correction. So this is the standardized regression equation. On the right hand side, these are the results of the unstandardized regression equation. So here the intercept is 0.606 and intercept is not significant because p-value is 0.737. That is, the t-statistic is 0.35, and then for x2 the coefficient is 1.35 and t-statistic is 3.04, and it is significant, 0.00. So this is a significant model. Standardized regression equation and unstandardized regression equation both reveal the same results. If the model is significant, it will be significant whether you compute standardized or unstandardized regression equations. That really doesn't matter. And you find ANOVA table. ANOVA table is testing what? ANOVA table is testing whether the model is significant or not. That is this relationship between y and x significant? Can I infer something about the population? Can I generalize it to the population from which the sample is drawn? So again, you see F statistic is very high, 60.7. On the left side, I think there is some table part is missing, and therefore it has been truncated, but it will be significant. And F is very high, 60.7. Whereas again, for the unstandardized one, you find the value of significance F, that is probability, P is equal to 0.006, which is much less than 0.05. The model is significant. So remember, ANOVA indicates the significance of the model. That is, it tests the significance of R square. Whereas t-test is for each variable. So later on, we'll use the same data when we want to compute R, and then we'll see how we can do analysis. And I have set another data set which you should do as a self-learning exercise by analyzing those following the commands that I mail you. So the line fit is now plotted. On the basis of the line fit, what we can see is that in the top figure, we are plotting x2 line fit, and we'll get this equation. This line fit is drawn on the basis of the standardized regression. There is no intercept, and we see that the observed values are distributed across the estimated model. So that straight line is the estimated model, and points are the observations. And we can see that most of the observations are they are in the near vicinity of the estimated line, and therefore that is why we got the model to be strong and significant. If they had been scattered like a circle in a circle, then there would be zero correlation. So, but now they are distributed across an ellipse, an oval, which is almost flat, which is almost, not fat, but it's very sleek, and it's across the fitted line. And for example, the value 14 is observed value is higher, but predicted value is lower. Predicted value is about 8 point something or 9. As you can see, the value of y at this dot, where I have shown this just below the observation number, where the value of observed value is 14, for value of y was 14, but here it is showing that it is about 10. So that means there is a large positive deviation or large positive error of estimate. Observation number 14 shows a large positive error of estimate because the observed value y is greater than the predicted value y hat. There's a positive. But if you go to the other one, where there's a negative y, you can see this observation where the value observed was 3 for the dependent variable y, observed was 3, but predicted is about 8 or whatever. So again, there's a negative. Now, one of the assumptions is that sum of all these positive and negative errors should be 0, because we assume that the errors are randomly distributed. That is one of the assumptions. We'll look at these assumptions when I come to multiple regression analysis. So what are the assumptions of the multiple regression analysis? first assumption is there is no specification error. That is, you expect a linear relationship, and that's right in the beginning I have stated that some people state the hypothesis for linear regression as, there's a relationship between X and Y, but they do not state it's a linear relationship that way. And then they do the linear, multiple linear regression analysis. So we should say that we must make that statement very clear by saying that we are postulating a linear relationship, and therefore there will be a coefficient of correlation which will be linear. That is the Pearson product moment correlation. So if you state a hypothesis that there is a relationship between Y and X, then you do OLS, on what basis? You are not testing the hypothesis. OLS, then you will have to do something like a polynomial regression. Use an OLS there, but it will be polynomial regression. So state the linear relationship, write the linear equation, and write in the beginning say that you are expecting a linear relationship between the variables. You don't get the results. That means linear relationship does not exist. So if linear relationship does not exist, no model can be good. No linear model will be good. You will have to go to polynomial models or some other kinds of models. Therefore, this is why, I am saying again and again, make a hypothesis that says that there is a linear relationship. Then there are no irrelevant variables included and no relevant independent variable excluded. So we have taken care of that. Now when we do analysis, this will be reflected in the analysis. We will see how it can be reflected. Then there is no multicollinearity. Multicollinearity means independent variables are highly correlated with each other. If the correlations between the independent variable are of the order of 0.9 greater, then if you look at the correlation matrix, if most of the correlation values are greater than 0.9, there's a possibility of multicollinearity. But still we should test the model for presence of multicollinearity. And there are no measurement errors. That is the scale that we have used to measure the variables. There are no errors. It has a high reliability. If you remember, in the last lecture when I talked about the error, if we increase the reliability, errors will reduce, because error is equal to, or reliability is equal to 1 minus errors. So error should be as low as possible. And errors will be low if you have a well-designed measurement scale, whatever measurement scales you are using for a certain construct, and error should be low. Of course, if there are no errors, then it's wonderful, but then you don't need any prediction. This is almost a functional relationship, like in physics. So you say velocity is equal to distance upon time, or speed is equal to distance upon time. That's a functional relationship, that's a mathematical relationship. There's no issue of making a prediction. But if such a statement you make in quantum mechanics, then you deal with probabilities. In fact, if some of you are doing, say, quantum computing, that is what you do in quantum computing. These are probabilistic results that you generate, and you see which is the most probable result, and you select that. A large number of results you are producing in quantum computing, and the one which is the best probabilistically the most likely model, that is finally selected. So I'll not go into that detail, but many of you must have done even in machine learning or in quantum computing or whatever have you. Now this is an important assumption about the error term, that above assumptions are met, then our estimate will be blue. This is called best linear unbiased estimates. So remember, if these assumptions are good, are met, then we'll get the best linear unbiased estimates. Our estimates will not be biased, and therefore we are already making a hypothesis that there is a linear relationship. But if these assumptions are violated, the linear relationship will not hold. So our estimates will not be blue. And if our estimates are not blue, then this model is no good. See, these terminologies you should remember, because if you now attend any seminar or a workshop or whatever, and people talk about these terms, immediately they should click in your mind that, yeah, I know what is blue. Blue means best linear unbiased estimate. They'll not say full term. They don't have time. In seminars, you get less time, or conferences, you get less time. And then there are certain other assumptions. Errors are random. That there is mean is 0. That we saw in case of when we did PCA, principal component analysis, or effective analysis, there we saw these assumptions. Variance across the levels of independent variables is equal. So it is not homoscedastic. So actually I should write, when I say across the levels, it should be homoscedastic. Now again, this term you will find some people pronounce as homoscedastic. Then the spelling is S-K, H-O-M-O-S-K. I'm pronouncing homoscedastic. It depends on whether you are from UK or for the US. Those people make those differences. So let's not worry about it. If you come across this term, homoscedasticity, it's the same as homoscedasticity. Then there is no autocorrelation. That is, the observations are independent. Error terms are uncorrelated. And we do some statistics called the Durbin-Watson. Most often this is useful when you see a time series analysis, because time series analysis are also all regression analysis. But there we observe certain values over a period of time. And then if you know the observations from 1 year to next year to next year, or one time period to next time period, etc., they are not independent. That means there's an autocorrelation present, and therefore something must be done to handle that autocorrelation. So in this regression analysis, we will not worry about autocorrelation, because we will not use time series or any other data where we'll have a long-term data collection. In longitudinal studies and time series data, this will become a very important consideration. That is, there is no autocorrelation, and observations from one time period or duration to the next, one generation to next generation to next generation, or cohorts. When you do study of cohorts, same sample studied over a period of time, longitudinal, etc., then there this problem will come. But for our understanding, for our analysis, we will not look at this problem. And then errors are normally distributed. Again, this is an important assumption, and if any of these assumptions are violated, our model will be no good. So neither we can make good prediction, nor we can make good theory out of that. So let's look at the multiple regression analysis. The equation is simple. It is now extended to a large number of independent variables, what we did for the bivariate regression. And BJs are partial regression coefficients. Now these are called partial regression coefficients because they are partial, because they, I suggest that you please read something about partial correlation coefficient. If you have 3 variables, and if you control one variable and find the correlation with the other 2 variables, you get partial correlation. So if you are doing a multiple regression equation, these B's are not simple bivariate correlations, but these are partial regression coefficients. So the meaning is that when we talk about B1x1, that means all other variables are constant. They do not contribute the correlation to this correlation between x1 and y hat. So x1 and y hat, the correlation between these two is partial out, or all other variables are partial out. They do not affect this relationship. That is why in multiple regression equation, BJs, the parameters or beta coefficients, they are partial regression coefficients. If you know the definition of partial correlation, as I have stated, partial correlation means if you have just 2 variables, you find a Pearson product moment correlation, for example, both variables are metric, you find R. But if there are many, you find R12.3. Remember, this is slightly different from multiple correlation. Multiple correlation, we find the correlation of one variable with all other variables taken together. In partial correlation, we find correlation between 2 variables with all other variables controlled for. So it doesn't matter. There are methods of computing those, but you don't have to worry because the software will produce these partial regression coefficients. And what are the tests of significance of B? For each one there will be a t-test. And t is equal to bj upon SEBJ. SEBJ is the standard error of that particular coefficient. And SEBJ is defined as 1 minus bj square upon n minus k, where k is the n is the sample size, k is the number of coefficients computed, including A0. So in a regression equation, how many parameters do you have to estimate? If you subtract that from the total number of observations, you get the degrees of freedom. And standard error of B is 1 minus b square over n minus k. 1 minus b square, because if you remember, in bivariate regression we defined 1 minus r square as the residual or the error term. You know, this is how we define the error term. 1 minus r square is the error term, unexplained variance. So if there are many, you take the beta coefficient of that particular variable. So for each variable there will be an error term. Error term will differ from variable to variable, but the degrees of freedom will remain the same because they belong to the same model. So for all of them, degrees of freedom will be n minus k, because we have estimated k parameters. Therefore, n minus k will be constant, and therefore t-test will be just the value of b divided by its standard error. Again, now some software will produce everything, but along with that it will also produce the significance results. So we'll see that when we do the analysis. So what is the test of significance of the regression model? I've been saying that we test the adjusted R square. First of all, we can compute adjusted R square from R square. There's a simple method of computing adjusted R square from R square. And R square test through F ratio. R square is tested through F ratio, and we can find this F ratio as R square by k upon 1 minus R square by n minus k minus 1. Simple, you know. If you want to do it by hand, so if you remember, I told you that I have done this analysis by using the Excel sheet, and where we have got these results. So if you are really want to be meticulous, want to understand things, you can use all these formulae and reproduce those results. So you can produce R square, you can produce R adjusted, you can see significance of R square, significance of beta, everything can be done. I mean, it depends upon how involved you want to be. If you are doing a doctoral thesis, then it's always a good idea to take a small sample. I have already given you the solution for that sample, but show that by using these formulae you can get those results, and then you should be very confident about it, and you can answer any question in the Viva or in any examination. Then we can also find the interaction effect of x1 and x2. Here it should be x1. So there are some corrections. Please note them down in the handout that I've sent you, and you should make those corrections in the handout. X1 and x2. So if we want to show there's a correlation, then we enter a term which is product of x1 and x2. If we want to say interactive and additive effects, this part is the additive effect, b1x1 plus b2x2, and this part is the interactive effect. Here in the interaction effect only, we don't enter x2. We don't postulate a model where x2 has a direct effect on the dependent variable, but only interaction, and the x1 has. But in the lower equation, we are saying that both x1 and x2 have direct effect and an interactive effect. So it depends upon your model. What model have you developed? On the basis of that, you should state your hypothesis. Now, major types of multiple regression analysis, you can, while doing the analysis, I'll explain again hierarchical, stepwise, etc. I'll talk about these in the analysis itself. Then there are different methods, forward entry, backward entry, etc. So I'll talk about them in the analysis. but there are some issues and considerations in multiple regression analysis. You may get the parameter estimates to be non-significant. And what can be the reasons? If you don't get significant results, model or the parameters, then these can be the possibilities. Sample size is small, that is one possibility. Generally, theoretically, the sample size should have at least one more observations than the number of parameters to be estimated. So if in any multiple regression equation you want to estimate 3 parameters, then sample size should be at least 4. But that is a theoretical point. It's trying to say that sample size should be larger than the number of parameters to be estimated. But 4, 10 or 20 observations or sample size of 20 or even that has no meaning. If you want to do a good research, because if you have a larger sample size while talking about the what is the unbiased estimate of mean, for example, mean is the unbiased estimate of a population. If the sample size is very large, it will approach that. Therefore, sample size should be large. And for every analysis, a sample size is determined on the basis of what level of significance you want, what statistical power you want in your analysis, what is the effect size, etc., etc. So those things. If you want to look, if you are looking at, say, earnings, then, and if you have children, university students or children also in your sample, then for them the earning will not be available. Earning will be available only for people with beyond a certain age group, because they start working at day. So there is a censored measurement or restricted variance in R because of whatever reasons, various reasons. And then multicollinearity. Collinearity I have already defined as collinearity is the strong or high value of correlation between two variables. When you have several variables, you call it multicollinearity. That's the only difference. So sometimes you will read the term collinearity. It should click in your mind that, yeah, we are dealing with two variables. If it says multicollinearity, yeah, we are dealing with more than two variables. Two independent variables or more than two independent variables. So what is multicollinearity? Common symptoms of high multicollinearity are substantial R square, but statistically insignificant coefficients. Actually, I should write non-significant. So if your model is significant, because R square is significant and R square is very strong, but none of the coefficients is significant, surely there is a multicollinearity. So make sure both should be significant. Then there's a great changes in regression coefficients happen if you add or drop certain variables independent. So if you have 5 independent variables, to begin with you took 4, then you added 5th one, and suddenly there is a great change in coefficients of all the variables, or you added 1. So all this but this is a feeble case of this multicollinearity. Then unexpected, large or small or nonsensical regression coefficients, very feeble. You expect certain range of parameters or regression coefficients, but they are very large compared to that or very small compared to that. Now that is very feeble, there may be some or they may not, but that's a very feeble symptom of the presence of multicollinearity. A coefficient with the wrong sign. So we expected a positive relationship between y and x, but the regression coefficient is negative. That means either our hypothesization, our theory is wrong, we stated a wrong hypothesis, or there is something happening. Therefore, again, this is a specification problem. You did not specify properly either the variables or the relationship between the variables, etc. Then there is some diagnosis for multicollinearity should be done. And we should check for bivariate intercorrelations. I had been saying it earlier. Should be, if it is greater than 0.0 between independent variables, then there is multicollinearity chances. Low tolerance, 1 minus R square for regression equation among independent variables. So suppose there are 3 independent variables, x1, x2, x3. I regress x1 on x2 and x3. Nothing to do with the dependent variables. I take these 3 independent variables, regress one of them on the remaining 2, and find out the value of r square. R square should be as low as possible. 1 minus r square should be as high as possible. Again, if 1 minus r square is about 0.8 or anywhere larger than that, then that means multicollinearity is present. So 1 minus r square should be as high as possible. Remember, r square should be large for the model, the regression model. But here I am saying r square should be small for a regression model that is between the or among the independent variables. So that is the difference that we have to keep in mind. There's nothing to do with dependent variable. Multicollinearity has nothing to do with dependent variable. We would like to have good correlation between the independent and dependent variables. That is why we will get strong model or significant model. But we don't want the independent variables to be strongly correlated, or there will be regression, will not be. So we can do that. We can regress x1 on x2 and x3, regress x2 on x1 and x3, regress x3. But we don't have to do this. There are some definitions, tolerance and variance inflation factor, VIF, and we'll compute that, and then I'll discuss what should be their range in order to infer whether multicollinearity is present. Then how do we combat multicollinearity? Increase sample size, mean center independent variables. Many people suggest that, but there's a question mark. You get the same results if you mean center the data. Mean centering the data, what it does is all variables have the same origin, 0. Because they are centered about the mean of that particular variable. So every variable has a 0 to begin with. And if we assume that we have defined 0, this goes well with the ratio scale definition. Then if every variable has a 0 which can be identified, then that's a good scale, a ratio level scale, and we are moving to the ratio level scale, and therefore our model will be good. And multiple collinearity can be to some extent avoided. But then there are debates about this. If you do mean center data or you don't do mean center data, then you'll find the same results. But if you have to do moderation, for example, if you do interactive effects and all that, there it may make a slight difference. Then combine correlated independent variables into a single indicator. You can do that by computing principal component analysis or factor analysis. So if you have 5 or 6 independent variables, and if there is a high multicollinearity between 2 variables, then you do a factor analysis of those 2 variables and find out one factor or one PCA by using surrogate scale or by using whatever scale you want to develop on the basis of that, combine them into one independent variable and input that into the regression model. And these variables are called offending variables. Offending variables are the ones which are offending your results. For example, you expect positive correlation, but regression coefficients, but you get negative regression coefficients, or they are affecting the whole model, etc., etc. So again, we'll see how we go about this process. I'll not do, of course, the factor analysis part that you've already seen, but then we'll see how, for example, and sample size increase is minimum requirement. And then we'll do analysis with mean center data, with original data, and then we'll see what we can do. And then how do we diagnose the presence of multicollinearity? Diagnosis is very important. We should diagnose which particular variable is the offending variable. If there are 5 variables, for example, in a regression model, then one variable may be the offending variable. And if we eliminate this, if we don't include this in our analysis, then the whole model becomes beautiful. Or if we combine that variable with some other variable, then probably, that correlation can be. Therefore, first of all, one is to infer, or one needs to test whether multicollinearity is present. If it is present, then which is the offending variable? We have to diagnose. So diagnosis and identification of multicollinearity are 2 different steps. And we'll talk about this when we do the analysis. these are some considerations. We'll use dummy variables for if you have non-metric data, for example, nominal, say gender or size of a company or level of management level at which an employee is working, or student education, for example. These are all the non-metric data. They are either ordinal or nominal, and therefore they should be converted into dummy codes. And I think I told you how to, why it is important. What are dummy codes? I asked you to go for self-learning. Auto-regression, I've talked about it. And the violation of additivity, normality, and homostaticity. Apply an appropriate transformation. If there are these problems, additivity, normality, and homostaticity, additivity model is y is equal to x1 plus x2. But if there's a term y is equal to x1, x2 into some product term, then additivity is being violated. The variables are not additive, they are interactive also. Then variables are not normally distributed, or there's a homostaticity, that the variances are not equal for all the variables that we have taken, independent variables. Then apply an appropriate transformation. I'll not go into this. There are methods of identifying which transformation will be appropriate and then using that transformation. There can be log transformation, inverse transformation, square root transformation, various other kinds of transformations. So that's a different lecture altogether. But you should, if you're interested, you should read that. Econometricians generally do that. They, for example, they find out log linear models or log models, or etc., and then they do an analysis, because either the relationship is not additive and not linear, there's polynomial, and then they took log. After taking log, they get a linear relationship, then they can apply ordinary least square solutions. But then the interpretation of the coefficients or parameters is not done in the way in which we are doing it for these models. So if any one of you is in econometrics and doing that, please understand that when we do a log-log transformation, then the beta coefficients don't define the strength of the relationship between a dependent and independent variable. But if it's a log-log, then it's simple, elasticity of y with respect to x. So that becomes elasticity. That is the interpretation of beta coefficients there. But fortunately, for most of the social sciences where we do simple ordinary least square, without any transformation of the data, this problem doesn't arise. But if somebody is interested in understanding econometrics and how do we interpret those models, either you read a text, good test, or contact somebody. Then graphical representation of regression models. This is very important. I think in the first lecture also I indicated how a theory-driven research can lead to, thinking about representation of models, and then we can represent what do we expect, what hypothesis do we expect. Now this is a direct relationship between x1 y and x2 y. So there's a direct, simple linear model, and simple equation will be, and hypothesis will be x1 and x2 are linearly related to y, and the equation will be as written at the bottom. And then, now this is a graphical representation of regression model where interaction effect is present. This is how you should write the model. See, this is important, that if you understand graphical representation of models, then the equation will be simple. You write down that equation, test that equation, period. Most often there's a problem because we don't try to understand. We don't want to make an image in our mind of the model, of the relationships. So remember, if I'm writing this, I as a reviewer can immediately see that you are interested in direct effects. That's all, period. You are not interested in anything else, and I know that this will be your equation. But if you're writing this kind of a model, as a reviewer, if I am reviewing your thesis or research paper, I immediately know that you're talking about direct as well as interactive effects. So these models are very, meaningful, and they imply lots of things. Now, this kind of model indicates that the relationship between y and x, there's a direct relationship, and also this is mediated by another variable. That is, x directly affects y. It affects a mediator which affects a y. That is possible. So now, you do a mediated analysis, and you find out three equations, like y. You find out these three equations: y is equal to cx, m is equal to ax, and y is equal to c prime x, when both the mediator and x is put into the equation. So what you put in the equation to find the value of c, you have a simple bivariate regression, y equal to cx. To find how much m is affected by x and then how much y is affected by b, you find out two equations. You find m because of x, so you write the bivariate equation m equal to ax, and then you write an equation where both mediator and the independent variable are indicated. So again, a multivariate equation, y is equal to c prime x for bm, and so on. Then you compute direct and indirect effects. Direct effect is from x to y, and that will be c prime when you are taking the final model, when everything is included in the model. C prime will be different, slightly different from c. So direct effect is c prime. To get indirect effect, you compute a into b. Now this should be standardized coefficients. So you use standardized regression coefficient to compute direct and indirect effects, and then you get the total effect as DE plus IE. Then you can find out what is the relative contribution of the direct effect. Divide direct effect by DE plus IE, the total effect, into 100. What is the contribution of the indirect effect? Divide IE by T. There can be two mediators, so there will be two indirect effects. The total effect will be one direct effect plus two indirect effects. Total indirect effect will be sum of those two indirect effects, and so on. You can extend it to any number of mediators. But generally, most of the good research will suggest one or two mediators and keep the thing simple for a research purpose, and then indicate how it can be extended to a larger domain. For doing doctoral research, it's always a good idea to take a simple model, but it should be complex to the extent that you can handle it with certain research ideas. And then you can generalize it by indicating how new variables can be added. Then relative contribution, I have already talked about. Then we should test also the significance of indirect effect. What is the significance of the indirect effect? For that we can do bootstrapping, or there is a test called Sobel test. Sobel test, these are the ways to compute. You can do it easily by hand, but then in the software I'll indicate what kind of results do you get. So Sobel test, as obtained by obtaining this particular value, AB upon SEB, where SE is the standard error, then this Sobel test, this ratio will produce Z statistic. And it's simple. If Z is greater than 1.96, there's a probability is 0.05. It is greater than whatever, 2.58 or whatever, then it's very strongly significant, high significant level. So those simple value of Z. Beautiful thing about Z is that degrees of freedom doesn't enter here. We assume a large sample, whereas in T statistic that is there. So Sobel test produces Z test. There is a moderating effect. That is, there is a variable which moderates the relationship between Y and X. So when we are talking about relationships between the variables, how something is happening, how are we getting Y because of X and Y? So is there a direct or immediate relationship? How and why? But if we are going to moderate it, and what is happening? Why is there something which disturbs this relationship? Either the relationship becomes stronger or weak because of the presence of Z, right? So you introduce a variable Z and you compute various equations. I think if you go through this slide, you will get an understanding of how this is done and how the moderating effect can be computed. So I'll just talk about this when we do the actual analysis of the data. We'll take up a very hypothetical, very simple example. Mind you, in analysis, I'm taking simple data, simple examples so that we can understand things. But that actually, in actual research, you should always take a large sample size and large. So there are two things. One is understanding things, and other is using or applying to data for a research purpose. So I want to make this point very clear. These lectures are to understand, but these will also apply. Whatever we understand here will apply to any amount of data. You can have 2,000 respondents. Doesn't matter. Same process will apply. But on the basis of small samples, we can see immediately. For example, in this small sample, we could immediately see as to what is the we could immediately see that there are some outliers. So observation number 6, 7 and 10. They are outliers. Their values very high. But if you have a large data set, you cannot just by eyeball inspection, you cannot find these. But there are methods. You can find out by applying those methods. So again, we'll apply those methods to this data. But the same methods will be applicable to a sample size of 1,000 or 5,000. That doesn't matter. That will be. So basic purpose is to understand what is there, what are the concepts, how will they apply, how will they help us in analyzing and utilizing and then interpreting. So this is just to summarize. You can have mediation analysis, you can have moderation analysis, and you can have moderated mediation analysis. The models can become very complex depending upon what is the need of your research problem, what do you really want to understand. So complexity is now going very high. Now, although people do simple multiple regression analysis for many of these models, and I think there's a paper by Barron and Kenny, which was much used 15, 20 years back, but there's a lot of debate about that, whether that is the correct way to do mediation. So please note down Barron and Kenny. If you can search from the Google mediation moderation analysis, you'll get a paper of Barron and Kenny. Otherwise, I'll locate it and maybe send it to you for reading, so that whatever I'm explaining here, you'll be able to understand that. So there's a reference from where I've taken the data, and so thank you for this part of the presentation. And now, shall we go up to another minute, or we meet at 1:30, madam?
Sir, we'll meet at 1:30. So till the time participant can have a break of 30 minutes.
Very good, very good. So at 1:40 कर लीजिए थोड़ा सा.
हाँ, perfect, sir. No issues.
So we meet at 1:40.
हाँ जी.
And then we'll do the analysis. This will be slightly longer. So please have patience. We can go up to whatever time, 4 p.m. or whatever.
Perfect, sir. Perfect. So participants
because I want to explain certain points there.
Okay.
Some points will be repeated, but some points will be new.
Okay, perfect, sir. No issue.
Okay, so 1:40 we'll meet. Thank you.
Okay, done.